Okay, so let's see where. Oh, here's a little problem that I can ask you to do. It's just sort of on page 221. Page 221, number 11. You have V equals 2 minus 3x. W equals 4 plus 5x plus x squared. What is 2V minus 3W equal to? So write down, calculate the answer, and then raise your hand one way or the other if you have when you have the answer. Okay. Oh, you have an answer. Sorry. Oh, I forgot. I was zoning out. Okay. Okay, Catherine, you have an answer. Good. Okay. Well, I think we're almost there, so I'll go ahead and start. Okay, we've got, now everyone can check me. So you have 2 times 2 minus 3x plus, not plus, minus 3 times 4 plus 5x plus x squared, which is going to equal 4 minus 6x minus 12 minus 15x minus 3x squared, which equals minus 8 minus 21x minus 3x squared. Now, the question is, did if your answer differs, who made the mistake? Is this algebra correct? Is this what you guys got, or did I get something? Did I do something wrong? Let's see. The constant term is going to be 4 minus. Is going to be 4 minus 12. Looks like minus. So this looks okay, right?
Yeah.
Okay. The linear term is going to be minus 6 minus 15. Minus 6 and minus 15 looks like minus 21. And the quadratic term is just minus 3x squared. Okay. Any questions or comments, or that's okay? This is the point here isn't to get the arithmetic. I mean, the point is that you understand what the process that you're doing here, that you're thinking of these as vectors, and these are the vector combinations that you could define these. Okay. So we have our examples. Now we can go and do some of this, but let's go on and look at the defining properties. Well, if we go through all those examples, they all satisfy these abstract properties. Okay? So these properties are what defines a vector space. So a vector space over the real numbers consists of a set V, where we have our 4 sets, or families of sets, along with 2 operations, a plus and a dot, which operate in such a way that for all vectors in the space and all real numbers, if I add 2 vectors according to this sum, it's still in the same space. That's just V is closed under vector addition, okay? They commute. V plus W is W plus V. And you can sort of see, we've seen that with, that's sort of built into a lot of the operations. It's associative. V plus W plus U equals V plus W plus U. The parentheses don't really matter. Okay, here's one. There's a vector 0 such that V plus 0 equals V. Well, we can go through each case and ask, well, for one in R3C, let me see what we call it. Yeah, 0 vector equals 0, 0, 0, right? For E3, your arrow is a point, an arrow of 0 length. And then in 3, it would be a polynomial vector V 0 equals 0 plus 0x plus 0x squared, right? And 4 would, let's say with 4 would be, let's say in the space M 2, 3, 0 would equal 0, 0, 0, 0, 0, 0. So in each case, there's a 0 vector that you can add. So there has to be the 0 vector. Okay, there's always going to be an additive inverse. Okay, then here's the ones that deal with numbers. You can multiply any vector by a number, and it's still going to be in the same space. And the multiplication of here distributes in the same way here. Well, this is an addition of numbers. This is an addition of vectors. This is a multiplication of a number times a vector. And the same way here. So these are two distributive properties. You can separate, this is an associative property. And this is sort of an interesting property. Otherwise, you have to connect up 1 times V is equal to V. That's an extra property. Okay, so so we're going to say anything is a vector that has these properties, no matter what it looks like, whether it's a column vector, a row vector, an arrow, a polynomial, or a matrix. And these come about, for example, in all kinds of concrete situations where you have sort of different sort of things that don't interact, that can move against one another freely when you model something. Okay, so but those are sort of defining properties. Now you can go through and one of the exercises in the text is to go through and verify for these big spaces. Like here, they just go through and verify that all of these things do work. Okay, we've actually done that before when you look at the properties of matrix addition. So a lot of you can just go through and verify these big spaces. It's a little bit tedious to do so. However, let's look at something a little different, where it's not so obvious that I told you that the solution of a linear system is also a vector space. Well, here is a linear system, 3 minus x equals 0 for x and y. And you can see y is leading and x is free. So we can solve for, or maybe the other way around. Let me see, what do I do here? X, well, it's sort of non-standard. Okay, but the point is that y is going to equal 3x. And so I've taken x as the free variable. And so I have this space here, L equals x, 3x, such that x is a member of R. Well, this is just a subset of two-dimensional vectors, right? But L is a vector space. That means that these objects all have the same properties. That means that I should be able to add 2 of these, x plus 3x plus y and 3y and get another element of this set. Well, what would this be? This would be x plus y, 3x plus 3y, but that equals x plus y and 3 times x plus y. So it is of the same form because this is a number, sort of like this is z and 3z, where z is equal to x plus y. This is just to show you, this is in the form of a number here and 3 times the number there. So addition works. Now, you don't really have to check all the other properties because these are already two-dimensional vectors. So we know they commute, we know they're associative, and also it includes the zero vector because zero is in here, right? So the place where this is interesting is when we have solution spaces like this and they're vector spaces. And it goes through and goes, laboriously or tediously through each of those properties and shows you that those all exist for this space. And let's see if there's what's going on. Oh, yes. Okay.
So we just use the associative property and find another number of the set.
Use the associative.
Oh, an example we just did.
Oh, the example here.
Yeah.
Oh, if we were to, well, we'd have to verify that held. That if I took 3 vectors and added them, it wouldn't matter which order. But we know that's going to occur because the addition that we've done is just normal matrix vector addition. We know that it's associated for all vectors, so it's particular, it's going to be associated for these. The crucial one is closure. Okay, now here's another example of a vector space we haven't come across, which is interesting in the sense that let's just do it here. We can have the zero space, which is just this set here. 0, 0. That's a vector space. It only has one element. It's the only vector space that has one element. We can see that, well, 0 plus 0 equals 0, right? And r times 0 equals r times 0, which equals 0, 0. And you can see from this that it is its own inverse. And so all the properties apply. So this is a vector space. It's the zero space. But it is a vector space. And that will turn out to be interesting or useful, okay? Well, sometimes it's called the trivial space, but we're going to just call it the zero space. And then you can look through and see what with the zero vector, what the negative is, and for our different examples. There are some other examples that are maybe more interesting for applications. For example, the set of these linear combinations of cosine theta, sine theta for a given theta. Well, you can see here you have an additional application. These things are for a vector space. How about this? All the solutions, this is a derivative, right? This is the second derivative of some function f. Take the second derivative of f plus f equals 0. So this is what you call a differential equation because it has a derivative in it. And so it turns out that the solution, that all the functions from R to R, such that this is true, form a vector space. As in general, it's going to be true. So this 0 here means this is called a homogeneous differential equation. This is a homogeneous linear differential equation. Well, a homogeneous linear differential equation, it's a family, it could have higher derivatives, but the solutions, all the functions that solve that equation themselves form a vector space. So if you find sort of like, in this one, it's going to be, if you find 2 solutions of this, you're going to be able to say all solutions are linear combinations of those solutions. So sometimes people take a differential equations course and they take linear algebra at the same time, and or if they're a differential equation, of course, they'll teach you a little bit of linear algebra because you use that in this. Well, it is a deeper connection too. When I solve linear homogeneous differential equations, I can convert it to an actual problem in linear algebra that I solve with Gauss's method, and then convert back. So there's more connections here between sort of calculus and stuff like that. Okay. Well, so that is the first, that's sort of the